Can people hear me?
Yes.
Yes.
Loud and clear.
Yes.
Okay, I'm going to, I think this will work. Is it time to start?
It is.
All right, so let's start. So this is the second lecture. I hope it goes better than the first one. I changed my setup a little better, so I hope it works. Last time we talked about the bias variance trade-off, and this is going to be a recurring theme in the class. That is, that the bias will tend to decrease, the variance will tend to increase. So we can find low bias models, they'll tend to have large variances and vice versa. There's also will be a flexibility interpretability trade-off. This won't be as hard and fast, but will tend to be the case that as flexibility increases, the interpretability will tend to decrease. Loss functions. We started talking about loss functions. We'll talk a lot more about them this time. There are many ways to measure loss or error, and which one you use may completely change your model. That is, the model may be dictated by what loss function you use. Today, I'm going to talk about something that some of you may have seen before, quantiles and quantile loss. And it will be an example of something where changing the loss function kind of changes the model you get. This will happen quite a bit. Up to now, most of you are used to using L2 loss, that is mean square error. Well, there are other kinds of loss you can use, and depending upon what you use, you may or may not be able to estimate the thing you want to estimate. I'm going to introduce you to the Newsbender problem, which is a simple problem that comes from operations research. It was solved initially by some economists, and it's the basis for all inventory management. And I've always thought that economists should know something about inventory management. We're also going to talk about classification today. Okay. Then we're going to talk about local models. Okay. I'll talk a bit about step functions. The very simplest kernel regressions, I won't call them that, and KNN regression, that's K nearest neighbor regressions. Finally, I'll talk about tuning parameters. And I'll briefly talk about cross-validation. I'll do more of that next time. Okay, so which loss function to use? And I'm going to give you an inventory example. Okay. We have demand for a product. Think of it as Nike shoes, maybe. And this demand has some probability distribution function. That is, we could answer the question, what's the probability the demand is less than 0? What's the probability the demand is less than 5 pairs of shoes? What's the demand that the demand is less than 100 pairs of shoes? And so on. And that's what that distribution function tells us. And we're going to assume that some statisticians or econometricians have already estimated that function for us. We're going to see that that isn't necessary, but we're going to start with that. Each unit is sold for a price P and purchased for a price C. So this is, except for the probability distribution function, this should be starting to sound a lot like a basic microeconomics lecture. Let I be the number of units stocked, okay? So I'm not assuming that you're going to have the number of units stocked equaled demand. That would mean you had a perfect model for knowing what the demand is. And so you're going to stock some units. Your expected profit is given by this, okay? Let's do this. Do red. Expected profit, okay? This is the important thing. So I have the demand, and I probably should have said I here instead of Q. Let's let Q, see if I can do this, be the number of units stocked, okay? So if I don't stock enough units, that's all I can sell, okay? If my demand is less than the number I sell, that I stock, that's all I can sell. I'm going to have to pay for what I stock, whether I sell it or not, but I'm only going to get the revenue from what I sell. And that will be the minimum of what I stocked in the demand. So if I stock 100 units and the demand's 0, I get nothing. The optimal inventory maximizes the expected profit, okay? And again, this should be a Q, okay? And it turns out that it can be written down very simple. You have price minus cost divided by price. You have the inverse function of the cumulative distribution function. We'll take a look at that. And the optimal inventory is given by that. So if you know F, you know P, you know C, then you will know how much you should stock in your warehouse. The question is, how do you know F? Or more importantly, how do you know F inverse? F inverse is called a quantile, and we'll talk about that in a minute. So that formula was called the critical ratio formula, and the function F inverse Z is called the Z quantile of demand, or the Z quantile of whatever that random variable is. And we note a couple of things. First, that the critical ratio has to be greater than 0 and less than 1. Why is that? Well, the price won't be less than the cost, because if that was the case, you wouldn't stock up. Okay? The cost won't be less than 0. If it was less than 0, you would basically buy a whole bunch of stuff, an infinite amount of stuff, and you would make money every time you bought something. Now, it's unlikely that the demand is constant. The demand will likely depend upon observables, price, prices of other goods, macro variables, all the usual things that enter in a standard demand curve. Okay? Hence, we would need to look at the following. So critical ratio again. Inverse distribution function conditional on X. I'm assuming you all know what conditional distributions are. If not, I can do a lecture next time on that. And we're going to write this as Q, P minus C, conditional on X. And what I would like to know is I would like to know what Q is. If I knew what that is, then I can just plug P minus C and X's into that function, and that tells me how much I should hold in my warehouse of that particular good. This is the conditional quantile of demand. How do you estimate something like that? Well, the way we're going to do it is we're going to change the loss function. Okay, I'm going to move this over here. I'm having to adjust my screen so I can see. So let y be a real valued random variable with some cumulative distribution function, f of y, which is simply the probability that the random variable is less than or equal to y. The qth quantile is given by the solution to a problem. That is, it is the inverse function of f of y. Let's see if I can, I'll come back here if I can't draw that on the next page. Yeah, so let me just note the following here, that this is f. Let's, I'm very bad at this. This is 1. And cumulative distribution function looks like that. And I am learning how to do this. So now I'm going to put tau down here, and I'm going to put q up here, and I have 1 here. And all q is f flipped on its side. So I just take this and I make the horizontal axis here, the vertical axis here, and the vertical axis here, the horizontal here, and vice versa. So it's just an inverse. And so how do we estimate those things? Well, I want to introduce you to the indicator function, okay? Here's a statement A. I of A equals 1 if A is true and 0 otherwise. Right. And now here is a loss function. It looks like a mess, but what we'll see is it's really not, okay? I have tau, okay? I have y here. I have the indicator function, okay? If y is greater than 0, y less than or equal to 0 is 0, because y less than 0 is not true. If y is greater than 0, then y less than 0 is not true, and the indicator function is 0. So rho of y equals t of y if y is greater than 0. If y is less than 0, the statement y is less than 0 is true. I of y less than 0 is therefore 1. And so it's tau minus 1 times y if that's the case, okay? So this is just a function for now. It turns out it's called something that's called the check function. I'll write it down here. Oh, well, there you have it. I will. Okay, so it's the quantile or the check loss function. A specific quantile can be found by minimizing the expected loss of y minus u with respect to u. So this is a term. So the quantile at tau is given by the U that minimizes the expectation of this loss function. The expectation is taken with respect to Y. And what this will turn out to be is something very much like what we do in a regression, except in a regression, what we do to get the regression is we minimize the mean square error. Here we're going to minimize something different. Okay. If we want the quantile to depend upon a vector of variables X, then we just simply replace the expectation with the conditional expectation. Okay. So to get a regression, what do? We minimize the square error. That is, we look at yi minus whatever our functional form is. Maybe that's an x beta or something. We square it. We sum over the epsilons. We sum over the i's, and we get our predicted value. To get a quantile, we minimize the check loss. Okay. So what I do here is I stick the quantile in here. Here's y. Here's my loss function, which we just talked about earlier. I sum that over all of the observations, and then I choose my prediction of y, of q of y, to minimize the check function. So depending upon what the loss function is, you get different things. So in the regression case, when I did this, when I summed over squared loss and I found the function that minimized that, I ended up with a regression, or an estimate of the expected value of y given x. With a quantile, when I minimize with respect to check loss, I get something entirely different. And so oftentimes your model will depend upon what your loss is. Now, here's what's important. Oftentimes people use squared loss because it's easy. You can do calculus with it. It turns out you can't do calculus with quantiles. That's why we have computers. And we will have other loss functions that we will use throughout the quarter. And I can't tell you the number of times I've seen people do an analysis that would have been correct if they had just chosen the right loss function. And we'll talk about this more when we get into examples. So if I take my loss function to just be something I'm going to call rho, okay? And if I take rho equals u squared, rho of u equals u squared, then the f hat we get is an estimate of the conditional expectation of y given x. Let's say that I take rho u equal to rho 0.5 of u and minimize with that loss. I get an estimate of the quantile at 0.5 given x. That's a conditional median. Okay. It turns out if your loss function was the absolute value of u, you would get exactly the same thing. Okay. That doesn't always happen, but it can. Okay. The conditional median. Here's another one that we will use later on in the course when we do support vector machines. And we'll talk about these over and over. So rho of u is the absolute value of u, just like this, but only if u is less than 0. So I could call rho of u minus u if rho is less than 0, and 0 otherwise. And it turns out that if you plot that with respect to u, like this 0, you get something that looks like that. So it kind of looks like a hinge. And that's why it's called hinge loss. We have something else called 0-1 loss, and we're going to talk about this in this lecture today because it's crucial for classification, for determining or modeling how people decide to go to school or not go to school, take a job versus not take the job, buy a large screen TV versus not buying a large screen TV. Okay? And it's rho of u is the indicator function, u equals 0. So if u equals 0, then this equals 1. If u is not equal to 0, then this is equal to 0. Now, let's look at the shapes of some loss functions. I'll share the code with this for this after you've done a little more R. Okay. So the green one is L2 loss. And you see that it is nice and U-shaped. Okay. Q.5 is the symmetric V shape, if you will. Okay. And then the quantile 0.7, one of the things you note is this is like the Q5, but it is rotated that way. The Q.1 is rotated that way. And as I said, the reason for bringing up quantiles at all here is that if you were ever to do anything in retail, you're going to spend a lot of time worrying about quantiles. And if you try to tell them what the mean is, they'll say something like, well, we really need the P80 level. And you go, what's the P80 level? Well, that's the 80th quantile or 80th percentile. And what that means is they want to kind of make sure with probability 0.8 that they can satisfy demand. So let's look at a non-parametric flexible model. Remember we talked about flexible models last time. Okay. Yi is a dependent variable. Xi is the independent variable, and now it's univariate. Okay. And I'm going to write my model as Yi equals f of xi plus an error. And this error is 0 mean. So note that implies that f of x is the conditional expectation of y given x. It's necessarily so. Okay, so here's an example. Okay, here's a function I just pulled out of nowhere, and I'm going to generate some data based on this, and I'm going to introduce you to your first kind of non-parametric models. I'm going to assume that we have errors that are normal with a variance of 0.01, so the standard error is 0.1. Okay. And here's some R code. You don't have to look at this now, but you're going to talk about R tonight, and I just thought I would show you what's going to happen here. So what I do is I say I want 100 observations. I create an independent variable and I sort it so the plots are going to look good. Here's my f of x, and here's adding the standard deviation times n, 100, normal random variables, standard normals. And then I'm going to plot y against x with the color equal blue. And there's the example, okay? So I simulated some data, and that's what the simulated data look like. Now, what I want to do is I want to add the graph of the true f. Now, in this case, I know what the true f is. Ordinarily, you're not going to know that. And so I plot the true value against x, type L, that means I want a line. I don't want the dots, and call equals color red. And if I execute this after a plot, what it will do is it will overlay this on the plot. Let's see if I can go back. Okay, so I have this plot with the blue. There's the plot. I execute a line statement after the plot statement, and it overlays the line on that. If you wanted a separate plot of that, you would have that same statement there, but you would say plot instead of lines. And if I hadn't done a plot statement before, it would say, I don't know what you're talking about because you haven't done a plot statement yet. So here's an example of, pardon me, plotting f by itself. So we plot the true function against x. We want a line, and I want it to be red. Okay. Now, I'm going to plot a step function. Okay. And you don't need to know the details here. This part is fairly advanced. But what I did was I approximated that function with a step function. Okay. And you can see that step function does a pretty good job of approximating that thing. So let's say that I had a point in here. Okay. The step function would say your approximation is right here. If I was here, it would say the approximation is down in here. And the point is you're going to be pretty close. You're going to be pretty close. So mathematically, I'm going to let Z0 through Zm be a uniform grid of points. I'm going to go back. Okay, and so basically what I'm going to do is I'm going to divide this up uniformly. Z0 is going to be fixed, okay? And then the next Z is going to be equal to the last Z plus H. So that means that Zi is going to be Z0 times I times H, and that's going to give me a uniform grid of points. This H is going to be really important later on. We're going to call that a bandwidth. And I'll test, and I'll talk about that later in the lecture. Okay. Now, let's let AI be a set. It's the set from Zi to Zi plus 1. So it's an interval, and note, I'm going to have it half open. And then I'm going to write this. I'm going to write G of Z equals A0, alpha 0, plus the summation alpha J times I, Z is in AJ. So if a Z that I'm interested in is in the interval AJ, then I of Z in AJ is going to be equal to 1. If Z is not in that interval, then this I is equal to 0. And so this is the sum of alpha I's times things that are either zeros or ones, and only one of them can be a 1. Why is that? Because points have to be in one of those intervals. Okay. That is a step function. Let's go back and look. Okay. So if you're in this interval, here's where you are. So that would be alpha 0. If you're in this interval, anywhere in there, that would be alpha 1. If you're in this interval, whatever height that is, that would be alpha 2, and so on. And this would be the last interval. And if you're in there, that would be alpha, whatever the last interval is. I forgot what I did here, 40. So be alpha 40. And if you're at this point, all of the other I's are going to be 0, except for you're in here. And the value of the function for anything in here is going to be equal to whatever that is. Okay, so that's the step function approximation to a function. And now I'm going to talk about a new estimation method. Okay. Let's say that you have a G that's the best step function approximation of F on the grid. And we won't talk about what that means yet. So that suggests that Y equals F of X plus epsilon can be written in this way. Okay. That is, I can take G of X, the best approximation, subtract G of X, so that's 0, that hasn't changed anything. And I can always write it that way. Then let's assume that this was really, really small. Okay. Let's say it's very much smaller than any possible G, and it's very much smaller than epsilon. Then I could rewrite this as G of X plus epsilon plus this small thing. And I wouldn't make too bad a mistake. Okay. And so my new error eta has 2 components to it. It has, and think to the last lecture now, it has an irreducible error, and it has a bias. So this approximation error gives you a bias. If you had a perfect model, G would equal F, and everything would be fine. So now we're going to act as though the approximation error is small enough to be ignored. If that's true, what I've said is that this is just a dummy variable regression. That is, these are the dummy variables. I'm assuming you all saw dummy variables in 482. I point out this regression is multicollinear. Why is that? It's because if I sum up all of those dummies, they're going to equal 1, and I've got an intercept here, and so I would have multicollinearity. That's because each observation is in one and only one interval, and every observation is in some interval. So you set it up as a regression in the following way. Let's set up the dummy variable dij, okay, is equal to 1 if xi is in interval j, and it's 0 otherwise. And so that means you're going to have, let's say I have 40 intervals. That means I'm going to have 40 dummy variables that tell me whether an observation is in one interval or another interval. So let's say I now regress y on the d's with no intercept. It turns out that that's going to be the formula for the ordinary least squares estimator. It's relatively easy to show that. I'm not going to have you derive this, but I want you to see how it happened. Turns out, this is important. Dij, what values can D take? 1 or 0. Those are the only values that D can take. Okay, so what's D squared? D squared is equal to D. Because, I won't write it, because D is either a 0 or a 1, okay? Now, let's say I sum up a bunch of things that are 0s and 1s. What do I get? I get the number of observations, or I get the number of Ds that are equal to 1. Okay. And what do I get here? Okay. This says I'm going to sum up the Ys, but I'm only going to sum up the Ys where the D is equal to 1. And so what this is going to give me is the following. This is going to give me the number of X's that are in AJ. So it's the number of X's that are in an interval, a common interval. And then what I'm going to do is I'm going to sum the Y's whose X's are in that A. Okay. That is, it's the average of the Y's whose X's are in AJ. That is a local regression. It's the simplest thing you can imagine. And it's relatively nice. Now, why I mention this is, well, for those of you who go to grad school, you're going to have to invent stuff like this. And I want you to see kind of the invention process. You know, you start with this notion and you say, well, you know, step functions work okay. You know, it looks like, you know, if I had the data all under a step function, I could just average that all up, and that seems like it would work. And that's how you get the intuition. And then the work starts. You have to prove it. We're not going to prove anything or very little in this course. This is called the local regression. H is called the bandwidth. The bandwidth controls the flexibility of the model. Okay, this is an important new term. The bandwidth is the tuning or a hyperparameter. Tuning parameter or hyperparameter. Some people call them tuning, some people call them hyperparameters, and they're going to be the thing that controls the flexibility of our models, the interpretability of our models, and the bias variance trade-off of our models. And we'll spend a lot of time learning how to tune a model. So back to the example. Oh, not back to the example. Sorry about that. Classification. So far we've only talked about regression. Remember, with regression, we're talking about the dependent variable is a cardinal variable. So 2 times something means twice as big. Okay. Now we turn to classification. So for example, our target now is a dummy variable or an indicator variable or a label. Y equals 1 if we purchase something, 0 otherwise. What is the expected value of this dummy variable? Well, recall what an expected value is. You take the value of the random variable, multiply it by its probability, take the next value of the random variable, multiply it by its probability, and keep doing that until you've exhausted all of the values and probabilities, and then you add them together. If you do that, you get a 0 here, and you get probability equals 1 times 1, or the probability y equals 1. And so this is a really important thing. That is, the expected value of a dummy variable is the probability that it's equal to 1. How to explain a dummy variable? What does it depend on? For purchase, what does the dummy variable did you purchase depend on? Well, it depends on price, prices of substitutes, other attributes, okay? And we'll all put those in some vector or list X, okay? And we will allow the probability to depend upon X. So our data are going to be now of the form yi, xi, I equals 1 through n, where now the yi's are equals 0 or the number 1. Okay? And this is considered now a label. So here are your economic variables, and here is whether you purchased or not. Here is whether you work today or not. Here is whether you work from home or not, and so on. Okay. The expected value of the y's is the expected value of y equals 1 given x. And so to explain stuff, I take an expected value and I replace it with a conditional expected value. And I'm going to write that simply as p of x. And we interpret the effect of x on y by looking at the effect of x on the probability. So in particular, we will look at the partial derivative of the probability of, say, purchase for a change in the price. And that's what our effects are going to be. They're going to be changes in probabilities. So let's say that p of x 0 equals 0.2. This is all well and good. I can interpret the derivative if I can take the derivative of the prices. But how does that predict y? So I tell you p of x0, because p of your characteristics, is 0.2. Does that mean you're going to buy the big screen TV or not? Does that mean you're going to work at home or not? How does that predict y? And this leads us to the Bayes classification or the Bayes classifier. Okay. So here's how we're going to predict. Okay. we're going to predict y0 will be equal to 1 if the probability at x0 is greater than 0.5. And we're going to say it's 0 otherwise. So that's my prediction. So I have a probability, I predict, or I estimate the probability, or let's say right now I know the probability. If the probability is greater than 0.5, then I say that y is going to be 1. If the probability is less than 0.5, or less than or equal to 0.5, then I assume it's 0. Now, what do you do with the greater than 0.5, less than 0.5, or equal to 0.5? You could just as easily throw it into the other class. I tend to do it with probabilities less than or equal to 0.5, but there are situations where you could imagine, pardon me, making this greater than or equal to. When you read a paper, it's really important you understand which they've done, particularly if there's lots of stuff at 0.5. Okay? Now, let's say I'm in a multi-class situation. There are I classes, okay? And the probability that I'm in class I, little I, given x, is given by pi of x, okay? So now we're talking about a situation where you can work at home, you cannot work at home, but stay at home. You cannot work, you can work but not at home, and other sorts of things. And there's a probability for each one of those things, okay? And now what I'm going to do is I'm going to say that yi is predicted as 1 if its probability is greater than all the others. So this should be all other j's. I'll just write equals not I. Okay? And you can only be in one class. Okay? So you can't be working at home and at home not working at the same time. If you can, then you have to create an extra class. Let me give you another example here. You have a die that you're going to throw that has 6 values on it. You want to predict the class, okay? Well, you're going to get a probability. And how do you predict the number of points with a probability? What you're going to do is you're going to look for the most likely class and assign somebody to that class. So if the probability of you going to Harvard is the highest of all the schools and options you had, I would say that you're going to go to Harvard. That would be my prediction. I could be wrong. Okay. By the way, if there are ties for that maximum, then you choose randomly. Okay. So let's say that 2 options are both probability 1/3, and all of the other options are less than that. And of course, they would have to sum up to 1/3. Then I would say the 2 options that are maximum, I would randomly choose between them, maybe by tossing a coin. If there are 3, then I would do something else to choose randomly between them. Okay. So this assumes that I know what the probabilities are. Oftentimes I don't. Okay. So I'm saying to you now, hey, is that person whose characteristics are X, is she going to buy a big screen TV today or not? And you say, well, you tell me the probability that she buys a big screen TV, and then I can predict. If it's greater than 0.5, then I'm going to predict she does it. And if it's less than 0.5, then I'm going to assume she doesn't, or I'm going to predict she doesn't. I say, well, I can't tell you what the probability is because I don't know. And so what that means is we're going to have to estimate those probabilities. And here's how we estimate probabilities. We estimate probabilities by noting that a probability is an expectation, and that to estimate expectations, we use sample averages. Okay, so let's simply try this. Okay, let's take the number of ones, the number of people that we observed that actually bought, divided by n, and this gives us the average number of people that bought a big screen TV, and we'll say that's our guess, p hat. That's our estimate of the probability. And if that estimate is greater than 0.5, we assume that you're going to buy. If it's less than 0.5, we assume you're not going to buy. And you say, well, you know, that's all well, good, and intuitive. But the problem is, well, I'm just pointing out something here. I'll get back to it in a second. Just pointing out that the expected value of p hat is in fact equal to that probability. And so it's an unbiased estimator. But here's the problem. The problem is we don't want the probability that y equals x, y equals 1. We want the probability y equals 1 given x. That is, we want to know, given x's, what's your probability of buying a big screen TV. And so what we're going to do here is we're going to try a local model. We just talked about local models, and here's an application. Okay. Now this is a different kind of local model, but it has the same flavor. So I'm going to calculate the distance from x0. So x0 is the characteristics of the young woman in question. And here is the characteristics of each person in my sample, and I've observed whether or not they have purchased a big screen TV. Okay. And here is the distance. Okay. Now, in this case, I'm going to just take square distance. So this is going to be, say, the Pythagorean distance, the square root of the sum of the squares of those differences. Okay, that's going to be a distance. But I could do something else. I could do the L1 difference. I could take the sum of the absolute values of the difference. I could do the L infinity norm. That is, I could take the maximum distance between them. The point is, I can compute a distance from each one of the x's to the x in question. Okay. And now what I do is I take the k observations with the smallest distance. That is, these are the k observations that are closest to x0. And I'm going to call those the k nearest neighbors to x0. And I'm going to let n, x0k, be the indices of the k nearest neighbors. So I might find observation 5, 22, 75, and 9 are the 4 nearest neighbors to x0. And so that would be those indices. And I'm going to estimate this probability. How? I'm going to say, let me sum up the y's for those k nearest neighbors and divide by k. So this is the average number of purchases of big screen TVs for the k nearest neighbors to x0. And I'm going to say that, let's say it turns out that nobody with characteristics close to the young lady with characteristics x0 bought a big screen TV. Then I'm going to say, I'm going to predict she's not going to buy a big screen TV. Let's say everybody with characteristics like her bought a big screen TV. Then I'm going to predict she's going to buy a big screen TV. Let's say 40% of the people did. I'm going to say, nah, I'm going to predict she isn't going to buy. Let's say 70% of people within who are close to her, that is, they're the k nearest neighbors, bought a TV, then I'm going to say, yep, she's going to buy one. And you've just been introduced here to what's called the k nearest neighbor estimator. And it's one of the workhorses in nonparametrics and in machine learning. We use it all the time. It has a problem we'll talk about later in the course called the cursive dimensionality, which means it really doesn't work very well for anything in high dimensions. And when I say high dimensions, I mean x is bigger than 2 or 3. Also, it's not terribly interpretable. You know, you'd like to be able to say, well, what happens if I change x? Well, if I change x, this neighborhood changes and a whole bunch of other things change. Or maybe if I change x a little bit, the neighborhood doesn't change at all. Not much good at getting a derivative. I have a paper that we'll see later on in the quarter where I show how you can use this to actually do some nice interpretations, but again, only if you have low dimensional problems. This is the k nearest neighbor or KNN estimate. Okay, but again, we want to predict y. Okay, we have the probability and we estimate with an estimated probability. That is, y0 hat equals 1 if our estimated probability is greater than 0.5. This is called the Bayes classification rule with estimated probability. It's Bayes classification. It is not Bayesian statistics. Now, I have a measure now. I have an estimate. It's intuitive. How do I measure how good that estimate is? Here's one measure. This is why I introduced the indicator function. Okay. So I asked the question, was yi hat equal to yi? That is, in my sample, if I go and I predict what y hat I is, do I in fact get yi? Okay. So this is equal to 1 if I correctly predict. It's equal to 0 if I don't correctly predict. And I divide by n. Okay, that's the fraction of mistakes. It's a fraction of mistakes I made. Okay, now the point here is this is the training error. That is, this is the error when I use the whole sample. And if you remember from last time, we said, you know, we probably want to split our sample into two parts, a training sample and a test sample. And so let's see how we're going to do that with this Bayes classifier. Before we do that, I want to ask a question. What's the best we could do if we knew the conditional probability? That is, what is the lowest possible error rate? So this means if I know the probability, what's the lowest possible error rate? Well, the Bayes classifier assigns an observation to the class that has the highest probability for that observation, okay? So the largest error rate at x0 is going to be this, okay? It's going to be 1 minus the maximum of px 0 and 1 minus px 0, okay? So that is going to give you what the error rate is. Let's page down. Okay, its expected value is given by that when I make sure that I'm noting that this is y, this is y conditional on x, and then I sum in the population over all of the x's. Okay, this is the overall Bayes rate, and it corresponds to the irreducible error in the regression. Remember in the regression we had the MSE could be broken up into a bias squared, a variance, and an irreducible error. For classification, this corresponds to the irreducible error. That is, if you know what the probabilities are, you can't get any lower than this. What makes things higher than this? Well, you don't know what the probabilities are. You have to estimate them. Are you going to have an unbiased estimate? Not always. You may have approximation error. And so you could have a bias, you could have a variance, and an irreducible error. And you're going to see this over and over and over again. So what's the test error for a Bayes classifier using a predicted probability? Okay, we're going to split our data into a test set and a training set. Okay, and I'll give you some code to do that, but for right now, let's just split it in half randomly. Okay, and what I'm going to do is I'm going to say p hat train, okay, is going to be the nearest neighbor estimator in the training sample, okay? So what I want to be careful here is, you notice that this is I, okay? This is J. I better erase that. So you, whoops. Do that a little better. Okay. So that is a J there. There's a J there, but I here and I there. And so what I'm doing is I'm taking every observation in the training set, okay, and I'm going to say, what are the K nearest neighbors to the first observation? And then I average that, and that gives me a training set for the K nearest neighbors and so on. I do that for every observation in the training set. This is the in-sample training or estimated probability. I predict the training to be equal to 1 if this probability is greater than 1/2 and 0 otherwise. And my in-sample, what do I want to call it? My in-sample error is given by this. How often was the training estimate equal to the actual training observation? Note that I have only train observations here because I've split my sample. Okay, this is the in-sample training error. And if you were to use it, you would overfit. Now what I'm going to do is the following, okay? I'm going to take the test, okay? I'm going to take X from the test, and I'm going to calculate the K nearest neighbors to that test X, which wasn't in my train X, but I can still find K nearest neighbors to that. I'm going to average those up, okay? And I'm going to do that for every X and every Y in my test set. Note that these are the training data here and the test data here. Okay. This is the out of sample or test estimated probability. Okay. And now what I'm going to do is I'm going to say Y test or Y hat test. I guess I'll put it this way. Y hat test equals 1 if X hat, P of X hat test is greater than 0.5, where P hat of X hat test comes from this, where I am using the training data to estimate the model, but then predicting out of sample, okay? And the out of sample prediction, notice I have test here and test here, okay? So these are in the test sample, and I'm predicting out of sample, okay? That is the out of sample test error, okay? I'm going to do an illustration here. Consider a case where we have two features, X1 and X2, okay? And consider all the sets of values X1 and X2 such that the probability is just equal to 0.5. That is, the probability of buying a big screen TV is just equal to 0.5. And I could go through all possible pairs of values that gave me a 0.5. Okay. This forms a curve that's called the Bayes decision boundary, and I'm going to show that to you in a minute. Okay. Okay. So for any I such that this is less than 0.5, okay, we predict the Y to be 0, and any I such that this is greater than 0.5, we predict Y to be equal to 1. Okay, so here we have this in 2 dimensions. So this boundary here is the Bayes boundary. That is, if I know the probabilities, then this separates the X1, X2 plane into 2 parts, okay? A part that's predicted orange, a part that's predicted blue, okay? You'll note that everything below this line, the little dots are blue, so that means that's the area where you predict blue. Similarly up here, predict orange. Now, the zeros, the O's, are the actual observations. So even if you perfectly know the probabilities, remember you perfectly know the probabilities to get this Bayes probability line. Even if you perfectly know the probabilities, there are going to be some mistakes. There are going to be some errors. Okay, so here we have these 4 observations are misclassified. Okay. Similarly, the predicted orange is over here, the actual orange is here, and you notice that we have more predicted actual oranges that are misclassified than we would like. So let's say that orange indicates having COVID. This would be somebody who has COVID and was predicted not to have COVID. And so in 2 dimensions, you can look at this. And now I'm going to give you an example of overfitting and of underfitting. The Bayes boundary requires knowledge of the true conditional probability. We don't. Okay. So let's do a k nearest neighbor with k equal to 10. Okay. And we look at all the pairs where p hat x1, x2 is equal to 0.5. And this curve forms a KNN decision boundary. Okay, and here's what it looks like. So this is the same graph we had before, except the black is the KNN prediction line. And so you'll note the black is different than the orange, than the purple. Okay. It has 1, 2, 3, 4, 5, 6, 7, 8, 9 of the blues are misclassified. It has on the wrong side of the black line, it has 1, 2, 3, 4, 5, 6, 7, 8, 9 of the orange misclassified. And so there are misclassifications, but you'll notice that this black line doesn't really look that bad. You notice over here, it looks kind of bad. Well, one of the problems is there aren't any observations over here. Okay, so you knew what the probability was, and so you can come up with the purple line. When you don't know what it is, it just says, well, you know, there's nothing here. I'm going to kind of split the difference. Okay, so it's if you have lots of observations packed together that you're actually able to do a good job with KNN. Now, this is KNN equal to 10. Let's see, I have something up here I have to move. Oh. There we go. What if we tried a smaller k or a larger k? So here is k equal to 1. So I just take the 1 nearest neighbor to the observation. So they're basically just 2 things I average together. Okay. And this kind of wanders all over the place. And it's kind of overfitting here. Okay. Over here, when I have k equal to 100, so I take the 100 nearest neighbors. Okay. You get something that's very smooth. Okay. There are a lot of mispredictions here. A lot of mispredictions. A lot of mispredictions. This over smooths, and you're going to get, I'm going to say something that's less flexible, that looks kind of like a straight line. So it's going to be fairly badly biased, but the variance isn't going to be too bad on it. K equals 1 is overfit. K equals 100 is underfit. The choice of K is really important, okay? K here is the tuning or the hyperparameter, just as the bandwidth was. And one of the things we're going to want to know is, what is K? K determines the complexity or the flexibility of the model, okay? And we need some principled way to choose K, okay? More generally, we need a way to find the optimal K. And typically, what we're going to do is we're not going to use the same sample to choose K that we use to train the model. Whoops. We're going to, in fact, use what we call cross-validation. We'll call it K-fold cross-validation. That K has nothing to do with this K. And keep. And now I will come back here. And I did that really fast. So I would like you guys to tell me tomorrow or next time, in fact, just send me an email. This was too fast. This is what I worry about with me and doing slides. I just go through them way too fast. So this was taken from a lecture that I did on the board. I covered this, and it took an hour and 45 minutes when I did it by hand. This is, what, an hour and 15 minutes? So I think I did this too fast. As I'm saying, I'm learning this as I go along. Let me know if it was too fast, and I will slow it down. Why don't we break now and come back at 7:30, and Herbert will do the lab. He will talk about R and matrices and vectors. Again, one of the things I'll mention is with vectors and matrices, I use them for notation, very few computations with them. It's just I don't like to write things out in summation notation when I don't have to. And R uses as its base objects vectors and matrices. And so R, matrices, vectors all go together. Are there any questions out there as long as we have time?
I have a question.
Okay.
I was just going to ask, it has to do with when you were talking about the max error.
Yeah.
So how do you know what the max error is when you can't know the probability of X naught?
That's absolutely right. And the same thing happens in a regression. I can't really know the variance. I can estimate it, but I can't know it. And we will see how we estimate that max error, but you can't know it. You're absolutely right. You can't know it. It assumes you know what those probabilities are, and if you don't know what those probabilities are, you can't know it. But what it says is that you can't do any better than that, and that can't be zero. That's the takeaway there. That is, even if you knew what those probabilities were, you still would not necessarily be able to, unless the probabilities were 1, predict perfectly the outcome of a classification. Other questions? By the way, unless you're embarrassed, it would help me if you ask a question, if you put your video on, so I get an idea of who people are and what they look like. Why is this important? When it comes time to write letters of recommendation, it's kind of important for me to be able to visualize that person. Oh, that was the person that asked the good questions. That was the person who did this. That was the person who did that. That's useful. That's useful for me, and it's useful to you too. One of the things, if you want me to write letters of recommendation for you, you have to do well in this course, okay? But B, I kind of have to know you too, because a lot of you are going to do very well. This is an advanced course. You guys have excellent preparation for this course. There will be somebody who finishes first, and there'll be a bunch of people, right in there as well. And usually the grad schools want to know things like, how is it you can tell me that she's going to do a really good job here at MIT? And I can say, well, I got to know her pretty well in office hours and the stuff she wrote. And she compares favorably with so-and-so who we sent to MIT 2 years ago. And she's just driven as all get out. She's somebody who simply will not give up on a problem. And she tends to teach herself stuff. And by the way, I should also mention that, during the COVID situation, she went down and volunteered, and she was helping out at the hospital, and she was doing Uber drives to and from the hospitals to get people there and back, and so on and so on and so on. Well, I don't know that stuff, which is important for the grad schools, because what the grad schools want to know is the following. We know you're smart, your GREs are good. You come to MIT, are we going to add just a little bit more than you're used to at the University of Washington, and you're just going to break? Or is it the case that you're going to come here and you're going to go, yeah, this is harder than the University of Washington, but it isn't like I'm, running the restaurant on the side and doing all the other stuff that I was doing when I was an undergrad. I have, plenty of resources left. I'm not going to crash and burn. I also need to be able to say things like, he's really creative. How am I going to know that? Well, I hope most of you are writing honors theses or senior theses. That's pretty important. It's hard for me to say whether you're creative or not if you haven't done something like that. And so if you haven't, you have to find some way of letting me know that you're creative, so I can say, this person is really, really creative. She worked as a research assistant for the Hutch. And while she was there, she came up with this really clever way of doing classification where there are mistakes in the classification. That is, we actually didn't know whether this person had COVID or not. We thought she did, but she might have had something else as well. And she came up with a really good way of filtering all that stuff out, and we were able to estimate the probability somebody actually had COVID. I don't know that unless I've talked to you and you've let me know that. So for those of you who are thinking about grad school, it's important that you get to know the people who are going to write letters for you. You should try to have people that you took upper division courses from whom you got, 3/8 to 4 points in the class, and people who have placed people in other grad schools, because what we like to be able to say, is this is like Annie Hong, who we sent to Carnegie Mellon, and she's quite in the same league with her, or this is not as good as John Smith, who we sent to Stanford, but few people are, but very much better than Christopher Peters, who also has done pretty well at Stanford. And so I'm not really worried that he's going to do a bad job at Stanford. And I can say that because I've placed people at Stanford, and other senior faculty can do that because they place people at places. So it's important to have senior faculty, 400 level courses. The fact that you were the top in Math 126 doesn't impress anybody. The fact that you were the top in Math 424 impresses the hell out of everyone. The fact that you were the top in intermediate micro, that doesn't impress anyone. The fact that you were the top in Econ 400, that impresses people. The other thing, for those of you who are juniors, think seriously about if your math is at the appropriate level. Think seriously about taking the graduate micro and macro next year in your senior year. So there are students that do that. I mentioned Annie Hong, she did it. Connor Goldstick did it. So a number of the top undergrads are invited to do that. You have to go and talk to Fahad, and he'll kind of give you a test and say, okay, you can do that. You need a fair amount of math. You need a serious linear algebra course, multivariate calculus, probably both of them, real analysis. I realize if you're not a math major, it's hard to take the real analysis course, but real analysis is really essential. You should have a calculus-based probability and stat course. I think those are the 490 courses in the stat department. And you should have a serious computer science course. I think is it 141 and 142 or 142, 143? All of those things are becoming very important in graduate school now. The math always was. Most of us, I have a joint PhD in economics and statistics. Hal Varian, who is the chief economist at Google, has a joint PhD in economics and mathematics. Most people who do econometrics theory have at least the equivalent of a master's degree, whether they took it formally or not. So you need a lot of math in graduate economics. And so for those of you who are juniors, prepare for that. And those are the people who are going to write you the letters that say, yeah, this is an economist, but she finished second in the real analysis course, and I suggested her she should go do a PhD in mathematics, and she said no. That's the kind of thing you want from your in your letters of recommendation. Anyway, a big digression there. And any other questions? If not, I will get off here, and you guys can come back when Herbert's on. Good night for now. And I am going to